You might remember that back in week 4, we did problems involving equations of motion when we were talking about higher order derivatives. We did lots of other things involving higher order derivatives, but this was one. And at that point, the only thing we could do was draw the graphs of the acceleration, the velocity, and the position. We said we didn't have enough calculus to actually find formulas to tell us, for example, how far an object had traveled. But we promised that we would eventually have enough calculus to do that, and now we do. So let's just remind ourselves of our different functions here. We agreed to use s of t for position, v of t for velocity, that's the derivative of position, and then a of t for the derivative of velocity, or the second derivative of position, and we called that acceleration. We also talked about the ones that come after that. They had some funny names in that video back then. So let's do this example. We did this very same one back then. An object is launched vertically from ground level with an initial velocity of 49 meters per second. Once it's in the air, the only important force is gravity, causing a downward acceleration, or a deceleration if you prefer, of 9.8 meters per second with every second. We'd like to figure out what's the highest point that it ever got to. So back then we were able to draw the graph of its height, which was an downward opening parabola, but we weren't able to figure out its actual highest value. Now we can. So back then we started with the easiest of the 3 graphs, which was acceleration. So acceleration here is constant, and it's downward, so acceleration is negative 9.8. And if you think back to how we did the problems back then, we then moved on to the next graph, in this case velocity, the antiderivative of acceleration. So v of t is the antiderivative of acceleration. In other words, it's the antiderivative of negative 9.8. So do you know a function whose derivative is negative 9.8? That must be a function whose slope is always negative 9.8. So negative 9.8 t. Is that the only such function? No way. We know by now that there's infinitely many, and we get all the rest of them just by putting the plus c there. So in this case, can we figure out what the c is? Do we have enough information to do that? Is there something in the problem that lets us figure out what the value of c is here? So what's c? We do have enough information because we know the initial velocity is 49. So we know that v of 0 has to be 49. And if I plug 0 into this formula, I get negative 9.8 times 0 plus c equals 49, and that means c is 49. So our formula for velocity is negative 9.8 t plus 49. And if you look back to the graph you drew back in week 4, that's the equation of the line that you drew back then. It had a y-intercept of 49, and it went with a downward slope of negative 9.8. From that graph, we then went backwards one more step to the position function, s of t. And that's the antiderivative of v of t. So the antiderivative of this, negative 9.8 t plus 49 dt. You might also remember back then we promised you that if you had memorized some formula from your physics class for these sorts of equations, that we would have enough calculus by the end of the semester to figure out where that formula came from. And here it comes. We integrate negative 9.8 t. This is t to the first power. So we add 1 to the exponent. We get negative 9.8 t squared over 2. And when we divide by 2, the negative 9.8 becomes negative 4.9, and then the t squared. So if in your physics class you've all along been measuring this memorizing this negative 4.9 t squared, or memorizing in the English units of feet negative 16 t squared, or just general for gravity something like g over 2 t squared, this is where those numbers came from. They came from the fact that acceleration was constant. When you integrated it, you got a t to the first power. When you integrated that, you got t squared over 2. And so whatever your original formula was for the acceleration, for the gravity, you ended up with half of it as your coefficient on the t squared here. So if you've been wondering all these years where that formula came from, that's where it came from. 49t, its antiderivative is just 49's antiderivative is 49t, and then plus some constant. We've already used c, so let's use d. Can we figure out what d is? So again, is there something in the statement of the problem that lets us figure this out? And there is, because the object is launched from ground level, meaning that at time 0, the height is 0. So we know S of 0 is 0. So if I plug in 0 into this, negative 4.9 times 0 squared plus 49 times 0 plus d equals 0. That's only going to happen if d itself is 0. So now we have our formula for S of t. Negative 4.9 t squared plus 49t. What are we trying to do with this? We're trying to find the maximum. So how do we use calculus to find the maximum of a function? We take its derivative. Should we take the derivative of this function? We could, but I think we wouldn't be impressed at ourselves if we did, because we already know what the derivative of this function is, right? Derivative of this function is negative 9.8t. So we want to set S prime of t equal to 0. That means negative 9.8t plus 49, negative 9.8t plus 49 equals 0. And when we do that, we solve, we get t equals 5. Now, from the context of this problem, we know that this is going to be the maximum, right? The object is going up for 5 seconds is what this tells us. At that time 5, the velocity is 0, and then the object descends. But for the sake of good form, let's check to make sure this is the max, the way that we normally do. Like when we were doing all those optimization problems. So if we let 5 there, and then S prime and S. If we pick a number less than 5 and we plug it into our S prime, we get a positive, meaning S is increasing, so the object is going upward. If you pick a number bigger than 5, you'll get a negative. And so yes, it is the max. And have we fully answered the question? Not quite, because the question actually asked not when the max height occurred, but what was the max height. Back in week 4, we already knew when the max height occurred. That was at time 5. So the max height is, how are we going to find that? Well, we're going to plug this 5 into the height function, S of 5. So is S of 5, I know the S and the 5 look very similar. So if we plug 5 into this, negative 4.9 times 5 squared plus 49 times 5, and that will work out to 122.5 meters. So as promised, now we know how to find the actual equations for these sorts of problems. Let's do one more. So this is different than any one that we did back in week 4. We also did then something with a car driving. So a car can decelerate at 30 feet per second per second. That's how it slows down. In other words, with every second that passes, its speed decreases by 30 feet per second when you put the brakes on. So often at the scene of an accident, what will you see some police officers or accident reconstruction experts doing out there? They're measuring the length of skid marks that the car left on the road. So this car left skid marks 120 feet long before coming to a stop on its own, meaning it didn't crash into anything, it just came to a stop without hitting anything, its own volition. How fast was it moving at the moment the brakes were applied? That's what we want to figure out here. So we can start similarly to how we did in the previous problem with the acceleration, because that's the easiest one. So what should our acceleration formula be here? It should just be negative 30, because we're decelerating at a rate of negative 30. And then from acceleration, we can get to velocity. So velocity is the antiderivative of acceleration. So what's the antiderivative of negative 30? That's negative 30t plus c. And do we have enough information to figure out what c is here? What do you think? We don't know anything about the velocity really here, because in fact v of 0 equals c, and v of 0 is what we're trying to find, right? We want to find out how fast was it moving when the brakes were applied. How fast was it moving at time 0? So in fact, the value of c since V of 0 equals C, C is the number we are looking for. That's the number we want to find. So once we found the value of C, we're done. So don't keep going after you find C. That's the end of the problem. So we got V of t is this. And from there, we can go to S of t, just as we did in the other examples. So now we need to anti-differentiate negative 30t plus c. So the integral of negative 30t squared over 2. That'll be negative 15t squared. In class, I always try to get somebody to say that the antiderivative of c is c squared over 2, but nobody buys it. So maybe you probably don't either. C is a constant, right? So the antiderivative of any constant is just that constant times t. And then we need a plus. Can't use c again, so let's call it d. And do we know what d is? We don't actually know what d is because we're not told that what position the car is when the brakes are applied. As we'll see, it doesn't really matter. So if you want, for convenience sake, to let d be 0 here, that's fine. If you say d is 0, that means that the brakes are applied when that the car is at position 0 when the brakes are applied, and therefore it's at position 120 when it comes to a stop. That'll work out to be the right answer, as we'll see. We don't need to do that. We can just leave the d in if we like. So what do we do next? Okay. Pause the recording and try to figure it out on your own. What we don't know is the time when the car stops, and that's the crucial thing to figure out next. So when does it stop? And it will stop when the velocity is what? It'll stop when the velocity is 0. So we need to solve 0 equals v of t. So 0 equals negative 30t plus c. And if you solve that for t, you get t equals c over 30. And that makes sense because suppose that the car were going at 60 feet per second. If it decelerates at 30 feet per second every second, what does that mean? At time 0, it's going 60 feet per second. 1 second later, it's lost 30 feet per second of velocity. So it's gone from 60 feet per second to 30 feet per second in 1 second, and then down to 0 feet per second in 2 seconds. And look, if you take 60 over 30, you get 2. So this seems to make sense. So now we're almost there. So where is it when it stops? So where does it stop? So we said that S of 0 is d. So that means S of the stopping time, c over 30, must be what? If we were at position D when we put on the brakes, what position is the car at when it stops? It's moved 120 feet further, right? So d plus 120. And so this is the equation that we want to solve. S of c over 30 equals d plus 120. So we can plug c over 30 into our formula for s here. So this is going to become negative 15 c over 30 squared. So that's going to become, well, let's just write it as c over 30 squared. Plus c times t. So c times c over 30 plus d equals d plus 120. And so now this confirms that you could have chosen any value for d that you liked because the d's are going to cancel no matter what. So if you had said, I want the starting position to be 0, then the ending position would have been 120. If you said the starting position is 7, the ending position would be 127. You were free to choose whatever you wanted as the starting position because you know it's going to be the stop 120 feet after that. All right. We're almost there. It's up to us to solve for what? For c. C is the number we want to find. So let's simplify this a little bit. We're going to get negative 15 c squared over 900 plus c squared over 30 equals 120. But 15 over 900 is just 1 over 60. So this is really 1 over 60. So c squared over negative c squared over 60. If we want to get a common denominator, this is 2c squared over 60 equals 120. So we put those together. We get c squared over 60 equals 120. So c squared equals 60 times 120, 7,200. We're almost there. C is, do we need the plus or minus here when we take the square root of 7,200? If there weren't any context to the problem, sure. But we know that c is the object's velocity, the car's velocity. The car is going forward, so we only take the positive root here. So the square root of 7,200, and if you want to rewrite that nicer, 7,200 has got a 3,600 as a factor. The square root of 3,600 is just 60. So 60 square root of 2 feet per second is how fast that car was going. Who knew that your police officers had such skills with calculus here? And that works out to be 58 miles per hour. If you're living in America, that's how fast the car was going. You can convert that to kilometers per hour everywhere else in the world who uses a sensible measurement system. And now we have a check your understanding so that you can practice this idea on your own.